All right, so let's go to the next page. All right, the reason, as I explained, are for efficiency. And you're going to be seeing an example like within a C codes that we implemented assembly code and we compute the processing time for the assembly function and processing for the C code. You will see that the time that takes in to compute the same function as assembly is much less. And so that's one of the reasons. Then sometimes for low-level programming, we need to access registers. Therefore, we need to write the code in assembly. So that's the second best reason. And then if we're going to use a specific CPU instruction, which are not available in C, we sometimes need to write those code in assembly because there's no other way to do it. Reason against that might be like the compiler dependence. For example, if you're writing C, assembly within a C is high-level language, and we can, no matter what the platform is, you can just run it. Windows, Linux, different machines, different, bit length, that's okay. But once you incorporate some assembly within C, then that's going to be platform dependent. And therefore, it's not going to be portable. So these are the reasons against it. As I explained, interfacing with C can be done in two ways. One is using the inline assembly. So it means that you can directly write your assembly function within a C simply by putting an ASM in front of it directly. So it's very easy, but professionals always prefer to have that assembly codes, wrapped in a function, and then you call the function in C, and so that the compiler goes and compute the function and come back to C. So it's a preferred way to write the function of assembly and incorporate it in C, not the inline assembly. All right, so let's talk about, to understand how we can link these two different coding, we need to understand how C code, behave when it's converted into a low-level language. Meaning that what is the relation between the high-level language and low-level language in a already C program. So to understand that, we can, if you remember at the beginning of the semester, we said there is a way to convert C program to assembly. So we have done it for 64-bit architecture and for 32-bit architecture. We could have done it for NASM and MASM, two different syntax of assembly. So basically every high-level C language can be converted to assembly, because there are some conventions that always exist so that you can create the one-to-one relation between C and assembly. So what we are interested in this course is that since we want to incorporate assembly function within C, we want to know how this calling convention apply for functions within C. Basically, we want to convert a high-level C program like this program, and see when it is converted into an assembly, what are the relation between the main function and the main function, which is this one, and the function within it. How these two are, incorporated together in assembly. So this is our program here. This is the C program we have. And then we use the tools that we introduced at the beginning of this semester and convert that to these assembly functions. So this is the result of that assembly coming from this C function. So as you can see in here, this is our main function, and this is our sum function. These are within a same file for this program, because our main C function incorporated this sum function within a similar file. As you can see here, we have the prototyping at the top. We have our main function over here, and then we have the definition of our function in here, right? So once we convert this to assembly, so our function gonna be this, and this is our main program. And this part is for when we call the function. It's actually where we call the sum function. So let's see what is happening. You see that I have 4 arguments in here in the sum function, right? So once you include some argument in your function and you call that function, what happened in assembly is that those arguments are pushed into the stack. So as you can see here, 10 push into the stack, and then 8, 4, 2, and then you call the sum function. Therefore, then you're gonna be directed to somewhere here, and then sum gonna be performed, and then you're gonna be returning back to the function in here. So the conclusion is that the arguments are pushing into the stack in the reverse order. You see that we have 2, 4, 8, 10, meaning that 2 is gonna be the first element in the two gonna be the element at the top. Therefore, you can assume that when you have something like this, it's gonna be turned 90 degrees like that, and therefore you have your first, the last element gonna be pushed first. The last element in your argument gonna be pushed first. Push 10, push 8, 4, and then 2. So therefore, it's gonna be your stack gonna be similar like this. It's gonna be 10. This one gonna be 8. It's gonna be 4, 2. And then you call the sum function. Simply the sum function goes here. You are familiar with these two. We create basically a stack frame by pushing EBP. The previous value of EBP gonna be reserved, and your new base pointer gonna be the stack pointer. And then you start doing the calculation over here. So here is your calculation. So basically you move EBP plus 8 into the stack, which is gonna be the element at the top, it's gonna be 2. You put it in EDX, and then you add that value with then you're gonna move the second element, and then you're gonna add these 2, and then the third element, and then the fourth element, and finally you're gonna add them together, and the result goes to EAX. So this is important. So the only thing is important here is here. Meaning that when you call a function, the argument gonna be pushed into the stack, and then the return value gonna be saved into EAX register. Then you pop EBP, and then you return to a function in here. And at this point, you're gonna be cleaning up your stack for 4 elements, which is 16, meaning that you will destroy actually this value in the stack, 2, 4, 8, and 10. And then you continue doing the rest of the function. So one thing, to conclusion, what happens in C when converted into assembly is that the argument going to be pushed into the stack in reverse order. And once the function is computed, the result going to be returned through EAX register. That's the conclusion. So if we want to incorporate an assembly within C, then we need to follow this calling convention in C. So these are what we actually explain. So we call main as a caller, some as a callee, something that we have called to it. So this is what we talk about. So element gonna be stored in the stack in the reverse order. So therefore, first 10 goes into the stack, and then 8, and then 4, and finally 2. So these are the things that we mentioned. So A gonna be stored in EDX, B gonna be stored in EAX, then we add this A and B together, the result goes into EDX. And what we do, again, we move C into register EAX, and again, add EDX to EAX. By now, we add A plus B plus C. And then what we do, finally, we move D into EAX. And in here, we add the result together. We get A plus B plus C plus D, which in our case are 2, 4, 8, and 10. And then you can see that the result is going to be stored in EAX. All right, so let's summarize the calling convention for 32-bit architecture. So we said that the parameters or arguments of the function are going to be stored in the stack in reverse order. The caller, which is the main function, removes parameter from the stack once you come back from the function. So let me point you to that. So this is what we mean by the second line. So main is the caller. It's remove the parameter from the stack. When you add ESP by 16, basically you remove 4 elements from the stack. Return value is stored in EAX. Explain that C assumes that the following registers are preserved, meaning that if you want to use these registers, you have to push the values into this stack and assume that there are some values that are needed in them. So you have to store them before using this register in your function. Labels, normally as an underscore, when you call a function, an underscore comes before the label. For example, your print function going to be print like this. So when you call it like a print function, or when you have like some function, it should be like this. But as you can see in this implementation for GCC, we don't have this underscore. If you are using another compiler, you use like Windows compiler, then this underscore going to be appeared and you convert your C file into an assembly. So this is the calling convention for 32-bit architecture. Therefore, for 64 bits programming, the calling convention is going to be different. So therefore, if you want to incorporate in assembly programming 64-bit machine, then you have to follow this, the guidelines and rules for the 64-bit platform. Okay, so if you have a void function and you're calling that void function in C, it's not going to return anything that's expected. It's going to be nothing in EAX. If your return value is 8-bit, 16-bit, and 32-bit, that's going to be restored in EAX. If there are 64 bits, it's going to be concatenation of EDX and EAX. Addresses are also going to be returned in EAX. Floating point value going to be restored in this STO register, which is not the topic for our course. Floating point, we are not concerned with floating point in this course. All right. Any questions so far about C calling convention? So we still haven't said anything about this lecture. We just introduced some of the calling convention in C, meaning that when they're converted into assembly, how functions are communicating with the main program. Simple, just we said argument gonna be stored in the stack, return value gonna be returned in EAX register. That's it. You understand this too, then you're good to go. Now let's go to the next slide. Okay, we talked about modular programming last week. We said that, conventionally everybody kind of follow like modular programming, and this is for simplification of a complex program and code into a simpler one by dividing that complex function or program into a simpler numerically or complex looking function into a simpler one. To simplify that and to make a team of, a big team of people working on a similar project, we need to do the modular programming. We talk about test.c and fact.c and how these are, these two and the parameters between these two can communicate. We talk about extern prefix and the reason for that. And yeah, that's pretty much it. So this is about modular programming. Just a reminder of what they were. So that one was in C. This also, we have modular programming definitely in assembly. You're going to be having the same extern keyword and global keyword. So when you are in your main function and your variable are defined in other functions, use extern to tell your compiler, okay, these are defined somewhere else. And once you are in your function and defining this variable, which you know that's going to be used in your main function, you put the keyword like global like in the beginning of it. So this is what we talked about last week. And let's go through the first example for calling an assembly routine in C. I'm gonna call an assembly function or assembly subprogram in C. As you can see from here, we have our print_sum.c, which act as our main function. And then we are calling calculate sum in assembly. That's .asm. So here is our function, which we call. And in here, we intend to implement this function in assembly. All right, I guess my pen doesn't work, but I use my finger to like write something on the screen. Okay, so we said that this is the function, and this function going to be implemented in assembly. This is the sum function. We said that's going to be in form of a label. And if you take a look at this C program, right? So we have two arguments, A and B in here. And if you look at our implementation in assembly, we don't have those arguments. So where those arguments go? And because we're going to implement this sum function, you have to take A and B and then do some processing on them, and then they return the values into this main function, right? So where I can get those arguments and how can I return those values into C in the main function? Anyone has an answer for it?
Use the stack?
Yes, exactly. It goes to, so that's exactly correct. Okay. So once I calculated the sum, then how I return the value to the main function. You know? Okay, we'll come back. All right, as he's mentioned, so in C, it is very clear when we, call the function, and when we implement the function, we're going to be having those arguments clearly specified for us. But in assembly, it's not like that. You need to know the rules. And the rules in here is that those arguments are stored in the stack. So we say B, and then A, and we actually have this function. These are going to be stored in the stack in this order, in the reverse order, B and A, and then we call the function, right? And the next thing goes to the stack is the return address, which is going to be the next line address for this guy. And then right now we're at this point. At this point, we push EBP into the stack in here. And then what we're going to have is that move ESP to EBP, meaning that right now ESP is pointing to this location, and our new EBP also going to be pointing to this location. Now, so you guys remember this, right? So these are the standard things that we do. It's actually this equivalent to inter syntax, and this one is equivalent to kind of leaf syntax. So now our arguments are stored in the stack in this order. So we said that, okay, we assume here that EBX also has some values. So we push EBX as well at the top. Now EBX is going to be in here. We assume that since EBX, if you remember the calling convention for C, we said that EBX are preserved. Therefore, we store its value at this. So now ESP point to this location, and EBP point to this location. Now, let's see what we do in here. In here, we say EBP plus 8. Therefore, this is a previous EBP. EBP plus 8 going to be pointing to this one. And then we move it to EAX. And then next line said EBP plus 13. So it's going to be this location, B. So basically, this is A, this is B. Now, A is in AX, B is in BAX, and then we add them together. So A going to be added to B, and the result going to go to EAX. And then we pop the previous value of EBX. Now EBX going to be restored with the previous value. We pop EBP. So EBP going to again point to its original value, and then we return. So once we said we return, this return value, we're going to jump to this return value stored at this point. So we're going to return in here, and then we're going to be using printf to print off the result. So take a look at here. So here is our C, right? C basically going to be having our return value, which is stored in EAX. This is done automatically. This is a calling convention for C. So when you see this variable in here defined as a return value for our function, these two are kind of linked together behind the scene, meaning that whatever value we have in EAX, now it's in C. And then when you say printf C, the value of the sum at this point going to be printed out, and then the function going to be terminated. Is this clear for you guys? You have an assignment about this and you have a lab. So basically you need to know the mechanics between the C and the assembly. So as you can see from here, the connection between the sum function in here and the sum function implemented in .asm is not explicitly defined, meaning that our variables A and B are not explicitly defined. It is us that need to understand that. Okay, A and B are in the stack and the value is located in AX. Any question about this? Since we use this, all right. Let's go to the next slide. As you can see here, this writing gonna stay, therefore we need to clean that up. All right. Now we need to create a binary file or executable for our program. So how we do this? We can use our shell file, or we can use our make file to automatically compile, create the object file, and then link them together. We talked about this before. So we create the object file for this C file, and then that's the 32-bit architecture. We create the object file for our assembly file, and then we link them together. So here is our two object file. The output file gonna be this, and we link them together, and finally we run them. Any question about this? Okay, so we have practiced this before. And again, come back to this writing. It shows you how to run it. And this is the make file we talked about last time. Anyone has any question about the make file? So this is our make file. We talked about this before. To run it, you just type make and then you get the result. Okay, when you say make, then you run the print sum. And you guys gonna be getting the value, output value for this function. So your A is -4 and B is 12. What you get is 8 as a result. So your 8 is gonna be in here. So that's the summation of these two. Very simple and clean. No questions so far? You can post your question on chat if you have any. And then I take a look at that and answer your question. Let's go to the next one. See what we have. Okay. I'm thinking whether I can show you some program before I move on to the next. Let me see. right, let me move to VirtualBox. Okay, run my Ubuntu. Okay, you guys can see this one? Can see this page? The PDF, Lab 10?
Yes, Dr. Dooley.
All right, good. So this is a function that we would like to implement in Lab 10. So f of x of y, which is x divided by 2 to the power y. So we want to implement this function in C as well as in assembly. And then we want to use a clock function to measure the time spent to calculate f of x of y for two different implementations. One implementation is going to be using a C function, and the other implementation going to be in assembly. So we said, okay, implement this, then measure the time that taken by these two different implementation and tell us the time, execution time for each, and talk if the assembly one is more efficient or not. The way that you do it, before you go into your function, so you set up a timer. Okay, you measure the clock before you calling your function. And can you see this hand in here?
Yes, Dr. Dooley.
No? Okay. So you start the timer in here, then you call your function, then you stop the timer in here. You define two different variables, begin and an end. You subtract them, end minus begin, so it's going to be your time. You basically convert its type to double and divide that by clock per second. Each processor has some number of clock per second, right? And then from there, you can compute the time spent to execute this function. So this is the time spent to execute the time. I mean, for this function that you have over here. Now this function is the implementation of this guy. One time you implement it using assembly, and you measure the time. Another time you implement it in C and measure the time, and you then compare the time taken for assembly implementation and assembly time and C time, and see which one is more efficient. So basically, this is that. Let me see in my machine. Okay. I'm gonna copy this on my share folder. Was lab 10 here. It takes so much time. Lab 10. CPA task 1. Okay. You guys can see the Ubuntu terminal, right?
Yes.
Okay. So, okay. So this is my make file. as you can see here, since I have basically math.h, the header file in my C implementation, I need to add this -lm into my make file to create my make file. I explained this one in the lab. So when you guys want to basically write your make file, please consider that you need the -lm in your link command. Okay, say make. Okay, now our binary is built and the binary name is main.out. So if we run that out, so it asks me to enter value for X and Y. So what I want to do, I want to put some value, for example, 20 and 2. So as you can see here, so it computes the value. X is 20, Y is 2. Basically, we divide 20. We divide, let's see, we can write it over here. So f of xy is x over 2 to the power y. In this case, my x is 20, my y is 2. Therefore, my f function, f of xy, is going to be 20 divided by 2 to the power 2 is 20 divided by 4. So the answer is 5. So as you can see here, it says the value is 5, and this function computed by C. The time taken by C is this one, 165 microsecond. And next line shows the value computed by the assembly, which is 5, and the time taken is 2 microseconds. So if you go back in here, T of C for execution is 165 microsecond, 10 to the minus 6, and T by assembly function is 2 multiplied by 10 to the power minus 6, which is 2 microseconds. So you can see 165 compared with 2. So the time taken by C is much, much higher than assembly. So we want our function to be executed as fast as possible. Therefore, implementation in assembly is more beneficial. All right. Yeah, that's pretty much it. So these are the files that I have. I have one mains.c, and I have my another function. I call it nonlinear.asm because that's a nonlinear function. And then I implement it using assembly. So that's taken a lot less. So you guys need to think about the way, because what is the way that I can, divide some number by 2 to the power of something in assembly, which is very efficient. Think about that. It is only 2 lines of code for its implementation. You're going to be doing that in your lab 10. Question about this? Implementation, execution time. So all these points are explained in the lab. So you guys have access to the macro for computing the time. Hopefully on Thursday, on Friday, you guys will be able to implement this by yourself and see how efficient it is to use the assembly coding. Sometimes, not always, because the code written, I mean, the assembly code written by us or by those professionals that write the code for C, sometimes there's going to be their C code going to be more efficient than our assembly code. Okay. Come back to our implementation. Yeah, this is that task 1 of lab 10. Now lecture 12. Okay, so we are at this part now. So this time we're gonna be calling C routine or C function within assembly code. As you can see here, our main function is in assembly, and then we have our tools defined in C. For the sake of this example, we said that okay, let's have a sum function, and then have a print signed integer, print unsigned integer, and print hex for our number. So let's use this function within our assembly code. So okay. So as you can see here, this is our sum. We call sum, and then call this function. We call this, and finally we call this. So let's see how this program works. Okay, we first push 1 and -2 into the stack, and then we call sum. So this is our sum. As you can see here, sum is defined as an external function in assembly. So meaning that when the compilers come and compile this code, it sees this one as external sum, and it goes to the other file looking for this function and find it over here. And doesn't complain. So when we call sum, it's going to come to this function and see that okay, it needs 2 arguments like A and B. If you remember from C calling convention, so for A and B, it's look into the stack, and in the stack, it finds A and B, it compute A plus B, and put it in EAX value. Now, call sum is in the, we come back from call sum, that's return. Now we are in this line. Then we add ESP plus 8. Basically, we clean up the stack, we take up these 2 from the stack, and then we go to the next line. Next time, we have EAX. We push EAX. What is EAX? In EAX, we have the results of 1 plus -2, which is -1. We push that into EAX. Now we call print sign integer, which is this function. This function have 1 argument, and it directly goes to the stack, look for A, and get A in here, and print that value out in the form of sign integer. So basically, what's going to be printed out after this is going to be -1. Second one is unsigned integer. It's look into the stack, it find -1. This time, it's printed out as an unsigned number. And it comes back, and next time, we call this hex function. It's again look into the stack, find value of A, and then print out A as a hex value. So in this implementation, you know that when you call a function, first thing that it does is the enter command, which it push EBP into the stack and update EBP value by ESP. And therefore, the program automatically knows where these A and B are. So it counts for EBP pushing, and it counts for um, um, base pointer update. So it kind of direct its left into the current location for A and B. So finally, we add ESP4, meaning that the one that we push EAX when we come back, so the return value going to be destroyed, and EBP going to be preserved, and then EAX is the top element, I mean the result -1. When we say add ESP+4, we destroy that, meaning that we clean up the stack. And next, what we do is we push 1 into EAX and we call interrupt AD. And this is the code for exiting the function. All right, so let's go to the next slide. Any question about this? All right, okay, so this is a way to run the code. We basically, what we do is we just create object file for each of these file, and then we link them together. We can do this in shell file, we can do this in terminal, or we can write a make file for it. So basically, this is your first line, right? And then there's your second line. You create object file for my tools.ca, object file for this, and then you link them together simply this line. Okay, and then you run it using this syntax. Run it using this. Right. Finally, run it using this syntax and see what the results are. This is a make file for it, and these are the results. As you can see from here, so first one, we print out the signed integer, which is -1. And second time, it prints out this value for us. And so anybody knows what this value is? Okay, in here in the chat see that they said what is the D word pointer means. D word pointer when you want to take something from the memory, right? You always have the starting address in the memory, but how much you want to take from it and put in the registers. For example, for 32-bit machine, it could be 1 byte, 2 byte, or like 4 bytes, right? D words means it is 4 byte. Therefore, take 4 bytes from the memory and put it in the register on the stack. So this is the answer to Charlie's question. Okay, now, yes.
Sorry, Dr. Billy, the D word is this double word. You went over this in class, something like this?
Yes, right? Exactly. Right. All right, so anyone know why the second number is this weird number, 42949679295? So we said print out the signed integer and unsigned integer. The second one is the printout for the unsigned integer in our program. Is this one? It is this line. Oh, let me take that picture. So that weird number is the result of this. Anyone knows what that number is?
Is it the largest memory address that's possible in 32-bit?
It is -1. -1 in 32-bit machine. My pointer is still on. Let me. Okay. So -1 in 32-bit machine is let me write it, is 0x f f f f f f. It'd be 8f in decimal. You can see that the attribute number is this one. It is -1, which become f f f f f f f, right? So this is this number. So when you print out as an unsigned, it is basically the 32 bits register that fill up with 1. That's equivalent of that number. And then if you take a look at the third print out, we said that if you print out that number for us in hex, that's the reason in here you see that this is FFF value. Okay, let's move on to other thing. All right, so as an example 3, so we said that let's implement this function in assembly, write an assembly program equivalent to the following program. Then call function like scanf, absolute, and printf from the C standard library. So meaning that you're going to be writing an assembly program, which you will use C macros or C standard library function like scanf, absolute value, and printf function. So the implementation is given in here. So this is our C function, and let me unpick this. This is our C function, and we want to implement this in assembly. So basically, this is our assembly code that is equivalent to this C function, where we use the standard library function in our assembly code for simplicity purposes, because we don't want to write the function for absolute value. We don't want to write a function for reading number from the keyboard, and we don't want to write a function for printing. We just want to call those functions to do something for us easy. So you see that. So we put the argument into the stack, and then use this function, and this function are communicating with those parameters that are stored in the stack. You take a look at the scanf in C, you're going to be having some values in the scanf. For example, you're going to have like implementation of the scanf, and I say, okay, whatever you get for me, you store it as the integer, that's %b, and then I want to give an address of A, meaning that you put it in A for me. So this is the for in C, and you're going to implement this for in assembly. So what you do is that you push A. A is the location in the memory. So therefore is a pointer that you put in the memory, in the stack, sorry. It goes into the stack, then you push the format in the stack. So the scanf one, you call the scanf, it goes to the stack and look for these two parameters. It's considered the first, the toughest element in the stack as its format, which is this one. And the second one as an address to store the thing that it reads from the keyboard. So as you can see here. Therefore, it reads it and it put it in A, in here. Now A is populated with what you enter into the computer, right? And then you add ESP8, meaning that you destroy the two stack elements that you populate these two into it, so because you don't need you don't need it anymore. And then you go to the next line. So you see that push the word A. See that A, this is answer to Charlie's question. A is an address to a memory location. When we do dereference it with the bracket, we need to tell the compiler, okay, how many bytes you would like to put into the stack. Is it 1 byte, 2 byte, or it's 4 byte? So since you said the word is gonna take 4 byte and put it in one of the elements in the stack. And you know that each element in the stack is 4 byte. So it's perfectly aligned with that. So whatever we stored in A, you push it in there. Now the content of A is on the stack. So when you call the absolute value, right, then your function gonna take that element in the stack and complete the absolute value and put it in EAX register. So once it put it in EAX register, you clean up the stack, and then you push EAX into the stack. Why? Because you want to call the printf function, and printf function gonna take an element from the stack and we print that. So printf gonna be pushing EAX into the stack, push the word the address into the stack, and push the formatting into the stack. And then we call printf. Take a look at the printf implementation in C. You're gonna be seeing these three variables. And then call printf. It's gonna be printing out the absolute value of that function. And then we do the cleanup for the stack. And then finally, we call exit function, which means you put one into AEX, and then you call the interrupt AD, you call Linux kernel, and you kind of terminate your program. Okay, this is it. And next, you run it to get your result. Let me delete this. Okay, same thing as before. Since these are the standard library, use this to get the object file, and you link the object file with C libraries, and then you execute your program. This is your binary file. You execute it. You can write a make file for it, or you can write a shell file to do that for you. Okay, this is the make file. We talked about this before. Let's look at that.